All right, let's talk about AI. For the longest time, the race has been all about getting bigger and bigger. But what if the real key to smarter AI isn't about size at all, but about design? Today, we're going to dig into a new model that's built from the ground up to be smarter, not bigger. Let's get into it.
So, let's just start with a huge question. As these AI models get more and more powerful, are they also becoming just too massive? Too expensive? Too complex for anyone except for a handful of tech giants to even think about building?
Right now, we are smack in the middle of what you could call an AI arms race. The thinking has always been bigger is better, and that's led to models that cost an absolute fortune to train. This creates this giant wall, right? It locks out smaller companies, researchers, and maybe even the next big idea.
And this massive barrier to innovation, it actually has a name: the AI compute wall. It's that point where the sheer cost and the resources you need to build the next generation of AI gets so incredibly high that only a few players can even afford to play the game.
But what if there was another way? Well, enter Motif-2. It's a new open-weight model, and it is specifically designed to challenge this whole idea that scale is the only way to get to power.
So what's the secret sauce here? How does it do it? See, Motif-2 isn't trying to be the heavyweight champion of the world. Instead, it's positioned as a much smarter contender, one that's built for pure efficiency and performance.
The whole philosophy behind this model is just different. It's not about brute force, it's about elegant design, it's about architectural innovation, and it's about squeezing the absolute most performance out of every single parameter.
Okay, let's get a little technical for a second. The paper describes it as an open-weight model that's built for high performance on a tight budget. And the real key to its success? It's this combination of a smarter architecture paired with a hyper-efficient training system.
So let's pop the hood and take a look at the playbook. How exactly does Motif-2 pull off this remarkable efficiency? Well, it really just boils down to two core innovations.
First, they basically gave it a smarter brain, a totally new way to process information. And second, they put it on a smarter training plan, which makes the learning process itself way faster and more effective. Let's break those two down. The first big idea is a new architecture they call Grouped Differential Attention, or GDA for short. Think of this as the model's brain. Now, at the heart of any model like this is the attention mechanism. That's what helps the AI figure out which parts of the data are most important. GDA cleverly splits this mechanism into two specialized teams to make it even sharper.
The way GADA works is actually pretty brilliant. Just imagine a sound engineer at a big mixing board. One set of controls, let's call them the signal heads, turns up the volume on the most important stuff, the melody, the vocals. Then another set, the noise heads, actively filters out all the background static and distractions. This lets the model focus with just incredible precision on what really matters.
All right, so that's the brain. The second key is all about how the model learns. Instead of just dumping a massive, messy pile of data on it all at once, Motif-2 is trained using this really carefully designed curriculum, kind of like a student going through school.
And the training curriculum is structured just like a school syllabus. It starts with the basics, general English, to build fluency. Then it moves on to more advanced subjects like science, math, and code. And the final stage, which they call the annealing phase, that's like graduate level studies, where it just focuses on complex reasoning to really sharpen its analytical skills.
Now, powering this whole process is this incredibly efficient engine called Parallel Muon. This is a system-level optimization, and it's designed to make the actual number crunching of training massively faster by getting rid of redundant work.
So how does that work? Well, think of a really busy high-end kitchen. Instead of one chef doing everything, Parallel Muon is like the head chef, splitting up all the tasks among many different GPU chefs. It creates this perfect assembly line where talking and cooking happen at the same time, and it makes sure no single chef gets overloaded. The result is a much faster meal, or, in this case, a fully trained AI model.
So that's the theory, right? A smarter architecture and a faster training system. But does it actually deliver? Let's look at the results and see how Motif-2 really does punch above its weight.
And the results are, well, they're pretty stunning. On the math benchmark, which is a really tough test of complex, multi-step problem solving, the 12.7 billion parameter Motif-2 gets a score of 73.6. I mean, look at that. It significantly outperforms QN3, a model that's more than twice its size.
And it's not a one-off. We see the exact same story in another super important area, code generation. On the human eval benchmark,
which tests the ability to write working code from just a description, Motif-2 scores nearly a 66, leaving the 27 billion parameter Gemma 3 model way behind. This is a crystal clear example of punching way, way above its weight class.
Oh, and remember that training engine we talked about, Parallel Muon? Well, get this. The system delivered a 7.1 times throughput improvement over the baseline system. That is not just a little tweak. That is a massive leap forward in efficiency.
You know, the paper's conclusion really just says it all. This quote perfectly captures the core finding. Smart design can absolutely compete with, and in some cases, even beat sheer raw size.
So what does this all mean for the bigger picture? I mean, this isn't just about one clever model. This is about a potential shift in the entire future of AI development.
So why should you care? Why does this matter? Well, because it starts to tear down that AI compute wall we talked about at the beginning. This kind of approach makes cutting-edge research more accessible to more people. It allows for faster, cheaper innovation, and it promotes a more sustainable way to build AI. Ultimately, it proves that great ideas can be just as powerful as giant budgets.
And that really leaves us with one final, fascinating question to chew on. What kind of future can we build when the best ideas, and not just the biggest bank accounts, are what truly drive progress in artificial intelligence?